This leads me to my next question, because we're talking about primer fields. The sun, a lot of people say when the primer fields collapse, the sun will go into a low mode, like a...
low mode. Oh, okay, yeah, right.
And my curiosity is that how did you find this low glow mode information in historic data, and is there a way we can monitor it nowadays? What is scientists looking at right now to keep an eye on that particular situation?
One indication is that the sun continues to weaken is the larger coronal holes that we're seeing. In around 2007, they noticed some holes in the corona around the sun, and that caused headlines in 2007. Now we see bigger ones every day, and nobody even talks about it anymore. But what happened is the coronal holes that open up, that also allow larger volumes of cosmic ray flux to come to the Earth, which increases cloud formation, which increases flooding events, which increases drought events. All these things are happening. So that's one factor we can look at, that to project forward how far we are in that progression. I would say the tripping point will be in the 2030s, when we see the temperature of the solar surface itself diminishing. That's to me would be the tripping point to really watch for.
Okay, I understand that too. With not happening for a while, and you're right. The coronal hole situation is normal now. People see coronal holes and don't think anything about it, but this is really adding up to something big. The increase of coronal holes, the weakening of corona. I've heard that if the sun's output is at 40%, that's considered low glow mode. And right now, it's been speculated that we're somewhere in the 60s, the mid 60s, 70%. So, but you're saying that we could possibly, the tipping point for that particular moment is going to be sometime after the 2030s.
Yeah, right now, the sun, the radiated energy from the sun is 100%. It hasn't diminished yet.
Okay.
It diminishes about 1 or 2 degrees over the solar cycles, but the surface temperature of the sun is still steady as a rock. But once you lose the solar winds, when the plasma inflow has diminished to the point that the solar winds no longer steam off, then the surface temperature will diminish. And once it's diminishing, then you have to sort of look forward to the point. You have to be prepared, because then really nobody knows at which point the primer fields begin to fail.
Right.
Once they fail, they turn off.
That's it.
That's it. So I gave it 20 years. It's sort of an average. There's another measurement that I come up with when I look at the beryllium measurements. For the time of the start of the last ice age, there is a spike that went up from the interglacial to the glacial, and that's a 60% increase in the beryllium level. Now, if the beryllium levels are a linear reflection of the increase in solar cosmic ray flux, then we will be at the 60% level much sooner than the 2050s. The the Ulysses spacecraft also saw the solar cosmic reflux diminishing by 20% in 10 years. So wow. to get to the 60% level, we're about 30 years in. That makes it about 2030. That means that the start of the next ice age could happen as soon as the 2030s. Well, I kind of hope it's more like the 2050s. But maybe perhaps it's halfway in between there. These measurements are not exact measurements.
Right.
We see the 60% spike at the start of the last ice age. It might not be a linear relationship. The beryllium levels might diminish less than in linear projections. I don't know. There's too little data on that. But my 2050 forecast and the 2030 beryllium level projection, well, somewhere in that area. It could be in the 2040s. That makes it about 30 years from now. I think the 30 years from now is probably a good time frame to prepare for. And 30 years is plenty enough time to get the Earth ready for it.
Sure. And we understand, too, that a lot of this forecasting is based on historical data. And the part that's really sobering about everything that you talk about, that John Casey talks about, Valentina Zarkova, and other good scientists across the community, is that the data that we're getting now is lining up to historical minimums that we've had in the past. So I know Mari had another question since we're on that topic of carbon-14.
Well, actually, you sort of answered the question I was going to ask about carbon-14 and beryllium and how significant those measurements are in the cyclic nature of minimums and whatnot. My one question, when I was going through your website and your material, I found it interesting, because in this community, people very much agree that the Milankovitch cycle does have an effect on cooling, and there is that. Now, you said on your site that that's not so much to be a concern as, it's not to be as much of a concern as what's going on with the sun. What holes in the Milankovitch theory have you found to say that? I'm just curious.
The Milankovitch cycle theory, I guess you understand it. The big hole is that the total amount of solar radiation that the Earth receives doesn't change, no matter how the spin axis is tilted. It doesn't change the total energy received by the Earth. It causes some hemispheric distributions, minute changes, and it causes some seasonal distribution, minute changes too. But it doesn't change the total energy received on the Earth. Also, the eccentricity variations that the Milankovitch cycles also include don't change the total energy received on the Earth. It's always the same. So if we have the same energy received on the Earth, no matter what the circumstances are, it doesn't give us enough to go with to say this is causing the ice ages. Look at it. When the ice age starts, the difference is so dramatic that the entire world becomes uninhabitable. If you look at all the ice core records that we talk about, the ice sheets of Antarctica and Greenland, when the Ice Age starts, it starts steeply. It doesn't start gradually. It starts steeply. And when it ends steeply. The transitions are big and radical, and the Milankovitch cycles don't come anywhere close to it. Now, the Milankovitch cycles are, they look quite convincing, but I would say the cycles which the Milankovitch cycles incorporate, like the tilt axis wobbling and the orientation changing for the 1,000-year cycles and the 100,000-year eccentricity cycles, these are subsequent cycles. These are not causative. These what do you call it, orbital cycles, they become affected by the Ice Age itself. When the primal fields collapse, the entire electromagnetic geometry that affects also the orbits change. And so we will see that the eccentricity changes in the rhythm in which the Ice Age changes. It's not that the Milankovitch cycles are the causative thing. They are looking at effects of it. And that's why I say, forget about it. A lot of people saying, just forget about the Milankovitch cycles, because also historically they don't add up. If you take it back historically over a long period, they're sometimes 10,000 years out, and sometimes behind, and sometimes 10,000 years before. You can't have. Yeah, that's a big gap, and you can't have an effect before it supposedly happened. So I don't put any weight in it at all.
Situation.
One indication is that the sun continues to weaken is the larger coronal holes that we're seeing. In around 2007, they noticed some.
This leads me to my next question, because we're talking about primer fields. The sun, a lot of people say when the primer fields collapse, the sun will go into a low mode, like a...
low mode. Oh, okay, yeah, right. Holes in the corona around the sun, and that caused headlines in 2007. Now we see bigger ones every day.
And my curiosity is that how did you find this low glow mode information in historic data, and is there a way we can monitor it nowadays? What is scientists looking at right now to keep an eye on that particular